In the last lecture, we did several examples on applying first law of thermodynamics for a closed system while reading property values from tables. Today, we are going to continue with the same topic, but I'm going to talk about incompressible substance, ideal gases, polytropic process, and then application of first law when we have ideal gases. Now, before we do that, I want to clarify a few things we discussed in the last class. We discussed, for example, if say temperature and volume are given, okay, for a pure substance, then how to determine the state, whether it is subcooled liquid or it is superheated vapor. We talked about that. Now, one addition to that is, let us say what is given is temperature and internal energy, or say pressure and internal energy. Then how to determine based on this information what is the state? If U is greater than Ug, that means energy is higher than the energy of saturated vapor at the given temperature or at the given pressure, then it will be superheated vapor. So it's very easy to remember because high energy means it will be superheated vapor. If U is less than UF, that's low energy, energy is less than the energy of saturated liquid, then it will be subcooled liquid. Okay. And same is true if we have, say, temperature and enthalpy are given, or pressure and enthalpy are given. So in these cases also, we can compare H with HF and HG. If H is greater than HG, it will be superheated vapor. And if it is less than HF, it is subcooled liquid. And between HF and HG, it will be two-phase. Okay, so that is an addition to what we discussed in the last class. Now, along with that, sometimes we may have a situation. Let me give you an example. Let us say it is given that pressure is 25 megapascal and temperature is let us say 400 degrees C, and we have to determine the state. Okay, now if you try to find, okay, let me look at saturation temperature at given pressure at 25 megapascal. Actually, you won't find this value in the table because 25 megapascal is above the critical pressure for water. So there is, this pressure is not even there in the saturated liquid vapor table because there is no distinct phase change at this pressure. This is supercritical pressure. Okay, this pressure actually is greater than critical pressure. So you can't read saturation temperature from table. Okay, so the convention is, let me first draw a diagram. Let's say we take temperature volume diagram. This is vapor dome, and the constant pressure curves on this diagram, you know, those are like this. So this is for a pressure that is less than critical pressure. This is the critical point, and if pressure equals critical pressure, then curve will be like this. There will be an inflection point here, and if pressure is above critical pressure, it will go like this. It will be above this. So you see, there is no distinct phase change process for this. So but you can say that here it is liquid and here it is vapor, superheated vapor. Okay, but the convention is, if temperature, this corresponds to critical temperature. So if the situation is such that if pressure is greater than critical pressure, okay, then the convention is, if temperature is less than critical temperature, that means it is in this region. it is called subcooled liquid. And if temperature is above critical temperature, that means above this point, above this line, then it is superheated vapor. So that is another addition. So this will be the situation if you are given pressure that is actually supercritical pressure. So there is no data for saturation temperature in the table, but still this understanding we can use. Okay, so today first I am going to talk about what is specific heat. Specific heat is a property that characterizes thermal energy storage capability of substances. So different substances have different thermal energy storage capabilities, and how to characterize them, that is characterized by what is called specific heat. Let me give you an example. Let us say we have, this is 1 kilogram of iron, and we have 1 kilogram of water. Both are at atmospheric pressure, and say both are at 20 degrees C, and we want to change their temperature from 20 to 30 degrees C. So we want to heat them. Okay, so they are different substances, but we want to heat them by same amount. It turns out that for iron, the amount of thermal energy we'll have to supply is 4.5 kilojoule to take it from 20 to 30 degrees C. And for water, it is around 42 kilojoule. So you see, we are heating same amount of substance, 1 kilogram, by same temperature rise, 20 to 30 degrees C. But iron requires only 4.5 kilojoule, whereas water requires almost 10 times of that, 42 kilojoule. So which substance has more thermal energy storage capability? Water has higher thermal energy storage capability. Okay. So in order to characterize this, we have a property that is called specific heat. Now, how this specific heat is defined? It is defined as energy required to raise temperature of unit mass of a substance. So you can say 1 kilogram, 1 gram, or 1 mole, 1 kilomole, but it is per unit mass. Energy required to raise temperature of unit mass of a substance by 1 degree. Okay, that is specific heat. But actually this definition is not complete, because if you want to heat a substance, okay, by 1 degree, 1 kilogram of that substance, because heat addition, heat transfer, it depends on the path. So although we are increasing temperature by 1 degree, the amount of energy required to raise that will depend on the path. Okay, so this definition is actually not complete. So I have written here, it depends on the process. Okay, and here is an example. If we take 1 kilogram of helium, okay, and we want to increase its temperature by 1 degree C. So its temperature, let us say its temperature is 25 degrees C, we want to increase it to 26. And we can do the process in different ways. So one possibility is if we are doing it at constant volume. Okay, it turns out that amount of heat transfer required is 3.12 kilojoule. Another possibility is if we are doing it at constant pressure. For this case, amount of heat transfer required is 5.19 kilojoule. Okay, so you see, in both cases, we are increasing the temperature of 1 kilogram of a substance by 1 degree C, but the amount of energy required, amount of heat transfer required, depends on the process. For constant pressure process, it is greater than constant volume process. And the reason is that in case of constant pressure process, this piston moves as there is heat addition. So this heat addition has to increase the energy of the gas and also do work on the surrounding, because this piston moves. Whereas in this case, all this energy is going into all this heat transfer is going into increasing the energy of the gas. There is no work involved here. Okay. So now we define, so there are infinite possibilities actually of processes. This is constant volume, this is constant pressure, but there are infinite possibilities how you are increasing the temperature by 1 degree. But in thermodynamics, we are interested in two special cases. Those are the constant volume case and the constant pressure case. So I want to complete this definition now. So if we say energy required to raise temperature of unit mass of a substance by 1 degree when the process is executed at constant volume. So we are specifying the process. When the process is executed at constant volume, then it is called specific heat at constant volume. We write that as CV. This is specific heat at constant volume. Okay. And if the process is constant pressure process, we are doing the same thing, increasing temperature of unit mass by 1 degree, but at constant pressure. Then the specific heat is called specific heat at constant pressure. We indicate that as CP. So this is specific heat at constant pressure, and this is the number for helium as we considered here. Okay. So at this point, it may appear that Cp and Cv, because actually these are not properties, because properties are associated with the system, but it looks like these are amount of heat transfer for a constant volume process and amount of heat transfer for a constant pressure process. So actually it may appear that these are not properties, they are associated with the process. Okay, so I'm going to clarify that. And I'll also show that we get this equation for CV. CV is del U del T at constant volume. So change in internal energy with change in temperature at constant volume. CV is that. And Cp is change in enthalpy with change in temperature at constant pressure. I'm going to derive this briefly. But after derivation, now I can argue that these are properties, because you see U is a property. U is a property of the system, and we are taking a derivative of U with respect to temperature at constant volume. So everything is a property here. So CV is also a property, and similarly Cp is also a property. Okay. And we also define specific heat ratio. I have used symbol K for that. Some books use symbol gamma for that. So this is defined as ratio of Cp to Cv, and this is always going to be greater than 1. Okay, because Cp is greater than Cv. So let us derive these expressions. Okay, so first let us consider a constant volume process. Okay, so there is heat addition, and if we write first law for this, like generally you write change in internal energy is Q minus W. Okay. Or if it is a stationary system, there is no change in the kinetic energy and potential energy, then delta E is same as delta U. So delta U is Q minus W. So this is the equation in the integral form. We can also write as delta U equals Q minus W. Okay, so these are uppercase symbols and these are lowercase symbols. The difference is we divided this equation with mass of the system. Okay, so this change in internal energy becomes change in specific internal energy, and this Q is heat transfer per unit mass. This is work transfer per unit mass. So we have to be consistent. Either everything is lowercase or everything is uppercase. So this is the integral form of the equation. We can also write this in differential form, which will be like du equals delta Q minus delta W. Okay, this is the differential form. And now we are writing delta for Q and W, and reason for that is because these are path functions. They are inexact differentials, whereas U is exact differential, so we write U for that. Okay, so that is first law. And if we apply this law for a constant volume heat addition process, this work term will be 0. So you will get du equals delta Q. Okay, if it is constant volume process. And see how CV is defined. CV is defined as amount of heat transfer per unit mass. Okay, so this is heat transfer per unit mass because this is lowercase q. Per unit rise in temperature, so I can write that as say if temperature rise was delta T because of this heat addition over delta T, or say dt at constant volume. Okay, that is the definition of CV. Amount of heat required per unit mass, per unit rise in temperature at constant volume. But this dq at constant volume is actually du. So what you get is CV equals del u del T at constant volume. Okay. Okay, so CV is a property now. So you can write CV as a function of temperature and volume, or as a function of temperature and pressure. Okay, because if from state postulate, if you fix two properties, then other becomes fixed. So CV is a function of two variables like that, or you can write it as a, yeah, write it in this way. Okay. Now instead of constant volume process, if the process is constant pressure, so now think of heating in a piston cylinder device. There is heat addition and it's constant pressure process. Okay. Then again, beginning from the first law, that is du equals delta Q minus delta W. In this case, there is work exchange because this piston is going to move when there is heat transfer at constant pressure. But we can combine these two terms, this boundary work term with du term, and that becomes dH. We talked about this previously also. So you get dH equals delta Q. Okay, for constant pressure process, for constant pressure heat addition. Now see, what is definition of CP? CP is amount of heat transfer per unit mass, okay, per unit rise in temperature when the process is executed at constant pressure. Okay. So this becomes, because this heat transfer at constant pressure is same as change in enthalpy. So this becomes change in enthalpy or change in temperature at constant pressure. Okay, so that is CP. Okay, and this is also a property. So you can write like CP is a function of say pressure and temperature, or it is a function of say temperature and volume. Okay, so like that. So these are specific heats. Okay. Okay, now I will talk about incompressible model for solids and liquids. In engineering, in solving engineering problems, we use several models which are approximations, but which are very good, because we don't want exact answers. We want an estimate which is a good estimate. And solids and liquids, although they are not perfectly incompressible, but their compressibility is very small, so we can treat them as incompressible. Okay, let us see, if we treat solids and liquids as incompressible, then what do we get? We get very simple results which are very easy to use, and as engineers we would like to use those results. Now incompressible substance means if its volume is constant, so it doesn't change. Okay, no matter you try to compress it or you try to heat it, its volume is not going to change, then it is incompressible. So solids and liquids are almost incompressible. It turns out that if volume of a substance is constant, it does not change, then internal energy is a function of temperature only. Okay. In general, you will write internal energy as a function of two variables, like a function of temperature and volume, or a function of, say, temperature and pressure. But for an incompressible substance for which volume is constant, we get U is a function of temperature only. And the derivation of this, the mathematical thing, actually, we'll see that later on. We need thermodynamic property relations to show this. Okay. Okay. Now, the definition of CV is del U del T at constant volume. But if U is a function of temperature only, when taking this derivative, we don't care about V because V is constant anyway. That is the nature of the substance. So you can write this as du dt. Instead of partial derivative, you can write total derivative, du dt. Okay. So now this means that because U is a function of temperature only, so CV also is a function of temperature only, because CV is du dt. So this thing is a function of temperature only. Okay, we get that. We are talking about incompressible substance here. So that is CV. Okay. Now look at enthalpy. Enthalpy by definition is U plus PV. Now the definition of CP is del H del T at constant pressure. Okay. So if we differentiate this with respect to temperature at constant pressure, you see V is constant, incompressible substance, and we are keeping P also constant. So this term is constant, its derivative will be 0. Okay. So del H del T at constant pressure will just become du dt, and it will be total derivative because U does not even depend on pressure. So it is du dt. So what do we get? It means that Cp, you see Cp is du dt, and Cv is also du dt. So we got Cp equals Cv for an incompressible substance. So we don't have to say Cp and Cv, we just say C. There is only one specific heat, and it is a function of temperature. It is not a function of two variables, it is a function of just temperature. Okay, so that is the result we get for an incompressible substance. So this you must remember. For an incompressible substance, there is only one specific heat, and we just call that C. We don't have to say Cp or Cv, and it is a function of temperature only. Okay. Now we got C is du dt, okay, or du is C dt. If we integrate this, du becomes delta U, and we can take the value of C at some average temperature. Okay, actually C is a function of temperature, so when you integrate this, C is inside the integral, but its variation is not very high, so we can take it outside at some average temperature. So delta U becomes C average times delta T. So we can use this expression for change in internal energy for an incompressible substance. So it's very easy to use. We just need value of C, and in the appendixes of various books, the value of C for various solids and liquids are given. Okay, so we can use this expression. And let us look at change in enthalpy now. H by definition is U plus PV. If I differentiate this, you get dH equals du plus, because V is a constant, we get V dP. Okay. And we integrate this expression, you get delta H equals delta U plus V is a constant, V delta P. So we can use this expression for change in enthalpy of an incompressible substance. It will be change in U, which will be C average delta T, or you just say C delta T. If the value of C is given, it will be just C delta T plus this term, V delta P. And this, the effect of this V delta P term, it is negligible for solids. For solids, we just neglect this term. Okay, for liquids, we may have to consider this. For liquids, there are various possibilities. Let me indicate those. Okay, we have delta H is delta U plus V delta P for an incompressible substance. For liquids, one possibility is, for example, say liquid is flowing through a pipe. and we want to determine what is change in enthalpy across the pipe, okay, as it flows. And if we neglect change in pressure, delta P is 0. There will be some drop in pressure. If that is negligible, that is 0. You get delta H is same as delta U. Okay, so you have to just remember this expression. This one is a special case of that, when pressure is constant. Okay, or other possibilities could be when, say, temperature is constant, and this happens when we pump a liquid. So liquid passes through a pump, and in pump there is negligible change in temperature. There is rise in pressure but negligible change in temperature. So because temperature remains constant, this delta U, that is C delta T, this term is 0. So delta H will be V delta P. So get delta H will be V delta P. Okay, so these are special cases of that. Okay, and let me also clarify one thing. So these equations are applicable only for an incompressible substance. So for example, let us say this is vapor dome, say PV diagram, and say the substance is water. Okay, it could be any substance, we are taking water. And say its initial state is here, 1, and say final state could be inside the vapor dome or could be here. Okay, I'm just taking, say this is the final state. Okay. And we have to determine delta U or delta H. Can we apply the equations we derived, C delta T or the equation for delta H? No, we can't do that. Because at state 1, it is incompressible. But it goes to state 2, and at state 2, it is not incompressible. Okay, so you're not going to use the equation. These equations are to be applied when it is incompressible throughout. Okay, so we can't do that here. So in this situation, you will have, what you will have to do is you will take H1 as enthalpy of saturated liquid at same temperature. We talked about this previously. Okay, or U1 as internal energy of saturated liquid at that temperature. You'll use table to get that, and similarly for 2 you are going to use table and then get delta U and delta H. But if the situation is you have state 1 is here, and let us say this is state 3, so it's water but it is incompressible, it remains liquid, so then you can use the equations we derived for incompressible substance. Okay, for solids you can always use those equations, because solid we can treat as incompressible. Okay, so we are talking about these special cases now which simplify our life very much. So in general you have to read all these values from tables, but if we treat the substance as incompressible, you see the life becomes very easy. Delta U is C delta T and delta H is delta U plus V delta P. So these are simplifications. Okay. Another simplification is ideal gas. And before I talk about that, we'll talk about what is called generalized compressibility chart. And this analysis is applicable for gases. It is not for liquids and solids. We are talking about gases. So if we define a compressibility factor Z as PV over RT, okay, P is pressure, V is specific volume, R is gas constant, T is temperature. And in this equation, temperature has to be in Kelvin. Okay, it can't be in Celsius, it is in Kelvin. Or this is also equal to PV bar. So whenever I put a bar, it means it is per mole. Let me clarify that. See this V, this is specific volume, its units are cubic meter per kilogram. Okay. This V bar, This is also specific volume, but instead of per kilogram, it is per mole. So its units are cubic meter per mole, or could be cubic meter per kilomole. So it is on a molar basis. Okay. And similarly, we have in the equation you see here, there is R bar. This is universal gas constant. Okay. This universal gas constant is, its value is, sometimes we indicate that as R bar or as RU. That is universal gas constant, and its value is 8.314. This you must remember, joule per mole Kelvin. Okay, so those are the units because it is on a molar basis. Okay, joule per mole Kelvin, that is why we put a bar here. It is on a molar basis, or RU, universal gas constant. Or alternatively, you can write as 8.314. It will be kilojoule per kilomole Kelvin. Same thing. Okay. Now the gas constant R is gas constant. This is not universal gas constant. It is different. This is universal gas constant over molecular weight of the gas. M is molecular weight of the gas. Okay, for example, what will be gas constant for oxygen? It will be universal gas constant, that is 8.314 joule per mole Kelvin. Divide this with molecular weight of oxygen. Molecular weight of oxygen is 32. So it is 32 gram per mole, or you can write as 0.032 kilogram per mole. Okay, 0.032 kilogram per mole. So you see this mole and mole cancels. So the answer you will get will be in joule per kilogram Kelvin. Okay, this is joule per kilogram Kelvin. So see, the gas constant is on per kilogram basis, whereas universal gas constant is joule per mole Kelvin. It is on a molar basis. Okay, so they are different. Okay, so if we define compressibility factor Z in this way,